Hi, Bobcats. In this video, we're going to take a look at the autoionization of water. This is an equilibrium that water molecules set up with H+ ions and hydroxide ions. This happens spontaneously to a very small extent. It's a very tiny number for the equilibrium constant. Nevertheless, it's something that we have to be aware of, and we're going to use it quite a bit as we do calculations on ion concentrations and pH. Our objective is to describe the relationship between the ionization of water and the concentrations of acidic and basic species in solution. This slide shows what happens to molecules of water in solution to a very, very tiny extent. A molecule of water will split apart to give us a hydrogen ion and hydroxide ion. So that's what's being shown here. This proton is going to transfer over to this water molecule, leaving behind this hydroxide ion and a hydronium ion. And so that's being illustrated three different ways. We're showing just regular chemical formulas in the first row. We're showing the Lewis dot structures in the second row. And then down in the bottom, we're showing space-filling models of two molecules of water undergoing this process. This process is known as the autoionization of water. Auto meaning that it's just automatic, it's something that spontaneously happens. The equilibrium constant for this gets its own special designation. Instead of a Kc or a Kp, we're going to call it Kw. Kw is equal to 1 times 10 to the negative 14. This is the only equilibrium constant that I will expect you to memorize. By the time you've worked a few problems in this chapter, you probably will already have it memorized. So that's not something you really need to put a lot of effort into. It will simply come to you. This autoionization reaction can be written a couple of different ways. The way we saw it on the previous slide was two molecules of water in equilibrium with H3O plus and OH-. Personally, I'm not a huge fan of the whole hydronium formalism, so you'll see me write it the second way, H2O in equilibrium with H plus OH-. If we go to write our Kw expression, if we write it based on the second equation, the shorter one, Kw is H plus times OH-. If we write it based on the first equation, we would write that Kw is H3O plus times OH-. H2O in that first reaction is a pure liquid, and pure liquids and pure solids don't appear in our equilibrium constant expressions. So Kw works out to be the same no matter which equation we use, as long as you recognize the equivalence of H plus and H3O plus. Remember that hydronium formalism with H3O plus is just trying to show that H plus ions don't really exist in water. They'll be associated with one or more water molecules. Yes, and then last but not least, 1.0 times 10 to the minus 14. That's an equilibrium constant you're going to use a lot. In this example, we're asked to calculate the concentration of hydroxide ion in a solution in which the hydrogen ion has a concentration of 2 times 10 to the negative 6 molar. Well, we're going to use Kw to do this because Kw is equal to the concentration of hydrogen ion times the concentration of hydroxide ion. And since hydroxide is the thing we're looking for, we can divide both sides of the equation by the hydrogen ion concentration, and that will give us the hydroxide ion concentration. Now, my 8th grade math teacher hated equations being in this form. If you solved for something, he always wanted to see the thing that you solved for over on the left-hand side. So I'm going to just flip this reaction around, this equation around. So I've got hydroxide ion is equal to Kw divided by H plus. And now I'm going to stick in the numbers. Kw is 1 times 10 to the negative 14, and hydrogen ion concentration is 2 times 10 to the negative 6. Now, When you run this through your calculator, please be very careful about how you're doing scientific notation. Remember, if we're going to do 2 times 10 to the negative 6, the best way to do this in your calculator is 2 EE, or depending on your brand of calculator, it might say EXP, and then your change sign key, and then the number 6. Do not hit times. Do not hit 10. When we're dividing by numbers in scientific notation, the calculator bites a lot of people, so make sure you're doing this correctly for your calculator. So we've got 1 EE 14 negative divided by 2 EE negative 6, and that is giving me 5 times 10 to the negative 9, and that's going to be molar for the hydroxide ion concentration. This question asks us to find the hydrogen ion concentration. Now it's labeled as hydronium, but every time I see hydronium, I just think H+, and I tip my hat to acknowledge that water molecules will be associated with this H+ ion. Since Kw is equal to hydrogen ion times hydroxide ion, or if you prefer, it's totally good to say H3O plus times OH minus. Now if I rearrange that equation to solve for the hydrogen ion concentration, I'm going to get Kw divided by the hydroxide ion concentration. Now if I plug numbers in here, Kw is 1 times 10 to the negative 14, and the hydroxide ion concentration is 8.9 times 10 to the negative 9. And again, when you run this through your calculator, make sure you're using scientific notation on your calculator correctly. So 1 times 10 to the negative 14 divided by 8.9 EE negative 9, and that's giving me an answer of 1.124 times 10 to the negative 6. For significant figures, it looks like we've got about 2 sig figs available, so that'll be 1.1 times 10 to the negative 6 molar for the hydrogen ion, or H3O plus if you prefer. Now that we've seen about the autoionization of water and Kw, one of the implications of this autoionization is that in any solution that's aqueous, you will have both hydrogen ions and hydroxide ions present. Now, I was used to thinking of acid solutions as having hydrogen ions and base solutions as having hydroxide ions. So those two thoughts are incompatible if you're telling me that every solution has both hydrogen ions and hydroxide ions. So here's the revision that we've got to make to the concept of acid and base. If we're talking about something being an acidic solution, yes, it will have both H+ ions and OH- ions. But if it's acidic, the hydrogen ions greatly outnumber the hydroxide ions. And they're related to each other by Kw. If we're talking about a neutral solution, we will have both hydrogen and hydroxide ions, but they will be present in an equal amount. Now, if we take that H+ equals OH- and we substitute into our Kw expression, what we will quickly find is that in a neutral solution, either hydrogen ion or hydroxide ion has a concentration of 1 times 10 to the minus 7. They are both equal to each other. And then last but not least, in a basic solution, the hydroxide ions outnumber the hydrogen ions. Any water solution always has both, but the relative amounts of hydrogen and hydroxide change depending on whether it's an acidic or a basic solution. So our objective here was to get comfortable with the autoionization of water. So it can be written as HOH in equilibrium with H plus OH minus. Whoops, that should be OH minus. And yeah, let me go ahead and erase that because that's really kind of weird looking. And there's a Kw that's associated with this, which is H plus times OH minus, and that has a numerical value of 1.0 times 10 to the negative 14. And that is the only equilibrium constant that I will not provide for you on a quiz or a test, but you will very quickly get that number memorized because you're going to be seeing it a lot in these problems.